Now that we've gotten a general understanding of the theory, let's try some numerical calculation exercises using the combined gas law. You'll recall during the earlier discussion I made a point to emphasize the term absolute. It's important to realize the combined gas law only works using numerical values measured on the absolute scale. You'll no doubt recall pressure is customarily measured using the gauge scale, meaning pressure above surrounding atmospheric conditions. 0 psi gauge is actually 14.7 psi above vacuum conditions. To convert a gauge pressure to absolute, one must add 14.7 psi. Unless specified otherwise, one can always assume any measurement in pure psi is a gauge measurement. Pressure using the absolute scale is specified using psi-A, standing for psi absolute. Similarly, temperature readings also need to be converted to the absolute scale, where 0 degrees is absolute zero. As with the scales Kelvin and Celsius, there exists a corresponding scale for degrees Fahrenheit, starting at absolute zero, known as Rankine, where 0 degrees Rankine is equal to roughly negative 459.7 degrees Fahrenheit. To convert a temperature reading in Fahrenheit to Rankine, one must add 459.7 degrees. Again, the combined gas law only works using numerical values measured on the absolute scale. One must convert given relative values to absolute, perform the calculation, and then convert the answers back to the relative scale for them to make any sense. Allow me to demonstrate. Consider a scenario where 1 standard cubic foot, or 1,728 cubic inches of air at 68 degrees Fahrenheit in sea level pressure conditions, is plunged to the depths of an ocean, also at 68 degrees Fahrenheit. Let's say the weight of the water overhead exerts 300 psi of pressure. In this scenario, temperature is being held constant. We know the pressure and the volume of the initial state and the pressure in the new condition. Let's see if we can calculate the volume in the new condition. Given temperature remains constant, we can remove it from consideration. P1 times V1 equals P2 times V2. Pressure went up, so volume should go down. Let's see if this is the case. We know P1, V1, and P2. We want to solve for V2. In algebraic manipulation, solving for V2 demonstrates that V2 is equal to P1 times V1 divided by P2. All we've got to do is substitute in the given values. Problem is, if we use these numbers in their present condition, we're going to get a garbage answer. We need to convert these gauge pressure readings to the absolute scale. 0 psi gauge is 14.7 psi absolute. Similarly, 300 psi gauge is 314.7 psi absolute. Substituting in these rescaled pressure values and our original volume of 1728 cubic inches demonstrates the original quantity of air has been compressed into a much smaller volume of 80.7 cubic inches, being a cube roughly 4.3 by 4.3 by 4.3 inches. Let's consider another scenario in which a balloon containing 1 standard cubic feet or 1728 cubic inches of 68 degree Fahrenheit air at sea level is put in a microwave, also at sea level, and warmed to 90 degrees Fahrenheit. In this scenario, pressure is being held constant. We know the temperature and volume of the initial state and the temperature in the new condition. Let's see if we can calculate the volume in the new elevated temperature condition. Given pressure remains constant, we can remove it from consideration. V1 over T1 equals V2 over T2. Temperature went up, so volume should also go up. Let's see if this is the case. We know V1, T1, and T2. We need to solve for V2. An algebraic manipulation demonstrates V2 is equal to V1 over T1 times T2. All we've got to do is substitute in the given values. Problem is, if we use these numbers in their present condition, we're going to get a garbage answer. We need to convert these temperature readings to the absolute scale. 68 degrees Fahrenheit in the Rankine scale is 527.7 degrees. 90 degrees Fahrenheit in the Rankine scale is 549.7 degrees. Substituting in these rescaled temperature values and our original volume of 1728 cubic inches demonstrates the original quantity of air has expanded to a volume of roughly 1,800 cubic inches. Let's consider a final scenario in which a rattle can of spray paint atomic vomit green with an internal pressure of 30 psi gauge at 68 degrees Fahrenheit is tossed into a campfire and heated to 300 degrees Fahrenheit. Just to make this fun, let's say the can catastrophically bursts at 50 psi. In this scenario, volume is being held constant by the rigid can. We know the temperature and pressure of the initial state and the temperature of the new condition. Let's see if we can calculate the pressure in the new elevated temperature state. Given volume remains constant, we can remove it from consideration, such that P1 over T1 equals P2 over T2. Temperature went up, so pressure should also go up. Let's see if this is the case. We know P1, T1, and T2. We need to solve for P2. An algebraic manipulation demonstrates that P2 is equal to P1 over T1 times T2. All we got to do is substitute in the given values. Problem is, if we use these numbers in the present condition, we're going to get a garbage answer. We need to convert both the pressure and temperature readings to the absolute scale. 30 psi gauge is 44.7 psi absolute. 68 degrees Fahrenheit is 527.7 degrees Rankine. Finally, 300 degrees Fahrenheit is 759.7 degrees Rankine. Substituting these rescaled pressure and temperature values into the equation demonstrates the pressure in the can is increased to roughly 64.4 psi absolute. We need to convert this back to the gauge scale. 64.4 psi absolute is roughly equivalent to 49.7 psi gauge. This is dangerously close to the can's bursting point at 50 psi. I'd suspect even the slightest tap would see the surroundings coated in a new shade of green. Alright, now that we've had some experience calculating the effects of pressure, volume, and temperature, I'd like to conclude today's lecture with a brief demonstration of some interesting phenomenon using all three properties and the complete combined gas law. Let's plot three properties on three separate charts. Consider a quantity of gas with a given volume and a given pressure at a certain ambient or surrounding temperature, V1, P1, and T1. These are the starting conditions. Consider what happens when we rapidly compress the gas. Volume decreases. As a result, the same quantity of gas molecules have less space to move around and experience more collisions with the side of the container and with themselves. In short, the bees get angry. As a result, both pressure and temperature rise. The smaller container, holding the higher pressure gas, feels warmer to the touch. Now sit back and just let the container cool to the ambient or external temperature of the surroundings. Note I've somewhat compressed the timescale for the slow return to ambient in the interest of saving space. After a period of time, the temperature of the gas returns to the original ambient temperature such that T3 equals the original temperature T1. Temperature has decreased, yet volume remained the same. Pressure slightly decreases. This being said, pressure is still higher than the initial P1 condition. Now rapidly expand the gas above and beyond the initial condition. Volume increases. As a result, the same quantity of gas molecules have more space to move around and experience less collisions with the side of the container and with themselves. As a result, both pressure and temperature drop. V4 went up. P4 and T4 go down. The larger container holding the lower pressure gas feels cooler to the touch. Now sit back and let the container warm up to the ambient temperature. Again, I've somewhat compressed the timescale for the slow return to ambient in the interest of saving space. After a period of time, the temperature of the gas returns to the original ambient temperature of the surroundings. Temperature rises such that T5 equals the original temperature T1. Temperature has increased, yet volume remains the same. Pressure increases. This being said, pressure is still lower than the initial P1 conditions. By all means, pause the lecture as long as you need to stare at these diagrams until you understand them on every level that I do. Two important fundamental actions can be demonstrated in this collection of charts. Compression decreases volume and increases pressure and temperature. Expansion, in contrast, does the opposite. Expansion increases volume and decreases pressure and temperature. Those of you that have ever used a pneumatic nail gun before have no doubt observed these same effects in real life. When the compressor fills the receiver becomes hot to the touch. When you open the dump valve at the end of the day, the expanding air cools, sometimes dramatically so. These rapid compression or expansion events associated with the change in temperature are known as adiabatic changes. You note that following an adiabatic change, there's always a return of the receiver to the ambient temperature, which results in a slight deviation in pressure than the initial compression or expansion event induced. This tiny deviation may be undesirable in certain applications. There also exist isothermal or constant temperature types of compression or expansion events, characterized by slow, purposeful compressions and expansions such that temperature remains constant and pressure isn't subjected to any last-minute temperature-induced deviations. Those of you with a hydraulics background will recall that pneumatic accumulators, energy storage devices in hydraulic systems, use a compressed gas in a flexible bladder to exert pressure on a confined liquid. Accumulators can be used to augment fluid flow, suppress shocks, control noise, or act as an emergency source of hydraulic power, among other applications. Rapid adiabatic charging or discharging of an accumulator ultimately results in the storage or release of slightly less hydraulic energy, whereas slower isothermal charging or discharging of an accumulator results in the storage or release of slightly more usable hydraulic energy. It's for this reason accumulator charging and discharging occurs at a slow rate, and sizing an accumulator for a hydraulic system must take these nonlinearities into account. The goal of slowly charging or compressing the gas in a pneumatic accumulator and the subsequent slow discharge or expansion of the gas is to not only store as much energy, i.e. pressure, as possible, but also to get as much of that stored energy out as possible. Lastly, those of you with a heating, ventilation, and air conditioning or HVAC background will recognize elements of the refrigeration cycle inside this diagram. Compression of a heat transfer fluid results in heat. Expansion of that same fluid results in cold. By strategically locating on which side of an insulated partition compression and expansion occurs, one could use this phenomenon to heat one space or cool another. One property important to technicians servicing pneumatic system is that of air's ability to hold moisture. I think the easiest way to illustrate these effects are with this chart. Air's ability to hold moisture is represented as the vertical y-axis, where a higher value indicates more moisture per volume of air, and a lower value less. As air loses the ability to hold moisture, water condenses out of the air and accumulates in the receiver, hoses, valves, or actuators in a pneumatic system. Temperature is represented using the horizontal x-axis. Given constant pressure P1, if we increase temperature, the air can hold more moisture. Conversely, given constant pressure P1, if we decrease temperature, the air can hold less moisture. In summary, warmer air holds more moisture, colder less. Now let's include plots for increased pressure P2 and increased pressure P3. Given constant temperature, if we increase pressure from P1 to P2, air can hold less moisture. Given constant temperature, if we increase pressure from P2 to P3, air can hold even less moisture. In summary, higher pressure air holds less moisture, lower pressure air more. As you're probably aware, only in very rare occasions do such isolated single property changes occur. During a rapid adiabatic compression, one might move from curve P1 to P3 at the same time moving slightly right along the temperature axis to find condensation forming in the reservoir. Steps need to be taken to rid the system of this accumulated moisture, either through routine draining of the receiver or the use of supplementary equipment like dryers. Similarly, during a super rapid adiabatic expansion, like opening a dump valve at the end of a workday, one might move from curve P3 to P1 at the same time moving dramatically left along the temperature axis to find moist air leaving the reservoir at such a reduced temperature it momentarily freezes and blocks the dump valve. As I hope I illustrated in this lecture, there's an interplay between volume, pressure, and temperature, and this interplay affects other properties, air's ability to hold moisture being but one. We'll examine air preparation elements like filters, lubricators, dryers, and coolers in later lectures. Until then, that's about it for today. In conclusion, this lecture examined the combined gas law. We learned compression events are associated with reduction in volume and a consequent rise in pressure and temperature. Additionally, we learned that expansion events are associated with increase in volume and a consequent drop in pressure and temperature. Last, we learned to distinguish between rapid adiabatic compression or expansion events associated with a change in temperature and slower isothermal compression or expansion events that occur at constant temperature. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.